Hello, my name is Ling. I currently work at the School of Civil Engineering and Architecture, Anhui University of Science and Technology. It's a great honor to receive the Best Research Award. Next, I will briefly introduce my award-winning work. My presentation will cover the following four aspects. Firstly, I will introduce the purpose and significance of our research. The drilling and blasting method is widely used in underground engineering construction, especially in tunnel excavation and milling operations. In the bench blasting of a large cross-section tunnel with poor geological conditions, frequent blasting operations can easily induce significant damage to the surrounding rock. This not only affects construction safety, but also poses hidden dangers to the long-term stability and operational safety of the tunnel. Therefore, it's crucial to analyze and propose a method to evaluate the blast-induced damage effect in surrounding rock. Secondly, let me introduce the research methods used in our study. In this work, we develop a numerical simulation method to investigate the surrounding rock damage effects caused by blasting in larger cross-section tunnels, while simulating the detonation process of explosives within surrounding rock prevents a relatively accurate and widely utilized method for analyzing blast-used damage effects in surrounding rock. It can become cumbersome and computational effects when simulating the detonation of numerous blast holes. To address this challenge, a simplification method in simulation proposed by the previous researchers was adopted in our studies. For the cutting holes per delay, the envelope line of the crack zone surrounding the blast holes can be treated as the equivalent boundary, with the prior history applied to it by equation 1 in PBT. For the breaking holes and smooth holes per delay, the line connecting the center of the blast hole can be considered as the equivalent boundary, with the prior history applied to it is determined by equation 2 in PPT. In our previous work, a damage constitutive model integrating the tensor damage model proposed by Yang et al. With the Drago-Prago yield criterion was established to simulate the blast-induced damage in rock. In the model, the rock damage variable is defined as the probability function related to crack density. According to Hooke's law, the incremental constitutive relations describe the damage factor can be defined by equation 5. When the rock mass isn't subject to tensor failure, the strength-stress relationship of rock mass is modeled by the Drago-Prago yield condition as equation 6 in PPT. Picture 1 provides a schematic diagram of the calculation process for blast-induced cumulative damage in surrounding rock. In this study, we employed the method shown in Figure 1 to simulate the cumulative damage of surrounding rock with different properties and the bench blasting of a large cross-section tunnel. Next, let me introduce the application of the developed numerical simulation method in practical engineering. We selected the long-line tunnel of China's high-speed railway as the research background. The Longlan high-speed river tunnel connects Jiangxi province with Shenzhen City. This tunnel is a single tuber, double-track structure spanning 10,244 meters in length, with a large excavation cross-section measuring 140 square meters. The four-phase blasting is deployed for excavating grade 2 surrounding rock, while the branching blasting is utilized for excavating grades 3 to 4 surrounding rock. Based on the blasting excavation of grades 3 to 5 surrounding rock of Longlan Tunnel, 3 symmetry have models for simulating the blaster-induced cumulative damage in surrounding rock are established. In the calculation, the surrounding rock with different mechanical properties is treated as an equal continuous medium. According to the simulated results, it is found that during the two-bench excavation of the tunnel with grade 3 surrounding rock, the blasting of the breaking blast holes closest to the excavation boundary has a substantial impact on surrounding rock damage. The damage depths are greater in the vault and medial floor compared to other locations with the smallest depths near the junction between the two benches. Following MS8 blasting, the damage variable at all locations reaches the max value. For the tunnel with grade 4 surrounding rock, the blasting of the breaking holes closest to the excavation boundary has a significant impact on surrounding rock damage, while the damage depths influenced by small holes blasting is minimal. The vault and medial sideway of the medial bench experience the greatest damage depths, followed by the medial floor with the smallest damage depths near the junction between adjacent benches. After MS7 blasting, the damage variable at all locations of the excavation cross-section reaches the max value of 0.98. For the damage with grade 5 surrounding rock, as the blast holes with different needs are sequentially detonated, the damage area of the excavation cross-section gradually expands towards the middle bench, while the damage depths at the junction between adjacent benches remains relatively small. Following MS7 blasting, damage is obvious at all locations of the excavation cross-section, with the damage vibration reaching a maximum value of 0.98. A lower method is the left figure for determining the critical peak particle velocity of surrounding rock damage, abbreviated as PPVCR, as was proposed in previous studies, considering the influence of inertial sequences on the damage and PPV of surrounding rock. According to the proposed method, the variation ranges of PPVCR for grades 3 to 5 surrounding rock are summarized in the following Table 1. From a safety perspective, the minimum value of across all locations is taken as the PPV CR to control the cumulative damage in surrounding rock. By comparing the values at all locations, it is determined that the PPV CR for grades 3, 4, and 5 surrounding rock is 16.8 cm per second, 13.7 cm per second, and 11.5 cm per second, respectively. Finally, I will present the research conclusions, which include 3 key points. As mentioned in the previous case studies, it will not be elaborated here again. Thank you very much.